Yes, again here is one problem, okay. We shall, first define a problem, then we shall solve a problem by introducing Dirac delta, okay. The problem is, I will take a vector field like this, okay. I will take a vector field like this. Vector field is equal to r cap by r square. R cap by r square. We have seen this one. This is this vector field is because of the charge at the origin. This comes in the electric field due to charge at the origin. Okay, no italic r. Okay, so normal r. So r cap by r square. Okay, let me take this vector field. So now we shall do one thing. We shall take its divergence. Okay, divergence of a vector field. Okay, del dot v. We shall solve it normally. I mean, you may have much more idea right now. Again, since this vector field contains only r cap component, okay, you better to deal with what you call spherical polar coordinate, isn't it? Because yesterday we have discussed the what you call the formula. Am I right? What was that? 1 by hr h theta h phi. I think dou by dou r vr h theta h phi plus other two terms, isn't it? So I can write it as again Vr into r cap plus 0 into theta cap plus 0 into phi cap. Can I write like this? Better to deal with this one. 1 by r square sine theta. I think dou by dou r. What is Vr? Vr is 1 by r square. H theta h phi is r square sine theta d theta, isn't it? Check this out. Sorry, why d theta came? R square sine theta, isn't it? H theta h phi is r square sine theta. Plus other two, again other two part we don't have to take here because other two contains dou some, so again just check that out. I hope other two will get cancelled, only this part remains. Because again other two contains v theta v phi, am I right that v theta v phi are 0? Is that okay? Since v theta v phi are 0, again you have to take only first term, okay? So deal with what you call, I think earlier we might have dealt with what you call Cartesian coordinate, but right now you have to make use of what you call formula, whatever we have discussed yesterday, okay? So now look at here, the r square got cancelled, derivative of sine theta, isn't it? I mean, so that is again, it's a partial derivative, or you can even take sine theta outside and you can write 1 by r square dou by dou r of 1, am I right? Is equal to 0. Divergence equal to 0. Let me only take this information. Okay, divergence of this above vector field is 0. Okay, just apply and find out that one. Divergence of this vector field is 0. Okay. Now we shall do one thing. We shall take origin here. Okay, we shall take this vector field and we shall find flux of this vector field, okay, through the spherical surface which centered at the origin. What is the rule? First draw the sphere, then draw the coordinate. Is that okay? X, Y, Z here. There is a sphere of radius capital R, okay? There is a sphere of radius capital R. So take the what you call surface integral of this one, I mean flux of this vector field through this what you call closed surface area. Let me take this one as closed surface area. Yes, okay. I need this one, surface integral of v bar dot dA bar. So over this surface, I mean which is a sphere, spherical surface which centered at the origin. Is that okay? Speak out. Now how do you deal with this one? So see the surface of the sphere, okay? I hope this is not completely a sphere. Yeah. Now, so take the what you call surface of the sphere, okay? So if you take the surface of the sphere, if you take a patch, okay, patch of area, okay, dA. So again, if you draw what you call dA vector, that dA vector will be along r cap direction, am I right? Speak out. Can you just imagine that one? This is r, this distance is r, this r is equal to capital R here. Origin to the surface, can you imagine? Origin to the surface, that's the radius, okay? So from the surface, again, if you define your dA vector, okay, because you need to do the surface integral over the surface, isn't it? So then your dA vector, what kind of dA vector that you are using, that is DAR, whatever the article formula we defined yesterday. What is that one? Speak out. H theta, H phi, D theta, D phi into R cap. Am I right? Or that dA vector, it is along R cap direction. It is radially outward. So can you imagine that one? Now substitute that one. Now look at here. Where you are taking this dot product, that you need to understand that one properly. Where you are taking this dot product, you are taking this dot product on the surface, am I right? Now look at here, on the surface, what is V vector direction? That's also along R cap, am I right? Check this out. V vector and area vector both are parallel actually, okay? And on the surface, okay, what is the vector field on the surface? Vector field on the surface, that's equal to R cap divided by capital R square, remember. These things are very important. I mean, everything is what you call kind of geometrical. Is that okay? Over the surface of the sphere, we have to substitute this one equal to radius of the sphere. Am I right? On the surface of the sphere. Now you just substitute this DAR and this V. Okay. Now look at here. This is equal to, again, what is this one? Speak out. R square sine theta d phi into R cap. Am I right? Again. Now we are defining that dA vector on the surface. That's why again this R square also that's equal to capital R square. Sin theta d phi R cap. Where we are defining this one? So we are defining this one on the surface of the sphere whose what you call radial distance equal to R. That's why again you have to put R square. When you substitute, look at here, R cap by R square dot product with what is this DAR? R square sine theta d phi into R cap again, okay? So closed integral. Actually it's a double integral, but we write only one integral symbol. R square got cancelled, R cap dot R cap is 1. Actually this is a double integral of sine theta d phi. Since it's a closed integral, theta should run from 0 to pi, pi should run from 0 to 2 pi. Then only that will cover the entire surface of the sphere. Can you get a feel of this what you call surface integral? Because we are going to use that one, okay, later in case of Gauss law and all. We are going to use that one frequently. Speak out. Vector field should be defined over the surface, okay? And then define area vector which is along R cap direction. You can see that one, isn't it? Wherever you take your area vector is radially outward, am I right? Radial outward, isn't it? Wherever you take, that's why that is DAR actually, whatever we have discussed yesterday. DAR, that's along R cap direction. Now what is this value? Solid angle. Do you remember? What is this value? Yeah, 4 phi actually. Is that okay? So I have elaborated this, what you call these things. So you try to have a feel of that one because it's very important, okay? Sometimes while I mean here this R is constant, okay? So when you move throughout this surface, okay, your R is constant, that's equal to capital R, that's what I have taken, okay? So here also you have to put so R equal to capital R, okay? That's not variable, you can see here in this surface integral, R is not variable, theta and phi are variable, okay? You can see that one easily. Yes, now look at here carefully, what happened here is, so this closed surface integral, okay, the same surface I am discussing, okay, of V bar dot dA bar, okay, so that's equal to 4 phi, am I right? But divergence is 0, divergence of vector field is equal to 0, okay. If you take volume integral, what is the volume? This is the volume. Volume enclosing the, what do you call, volume within the surface. Can I say like this? Volume within the surface. If you do volume integral of the divergence of this vector field, is that okay? D tau, that also should be 0. If this is 0, speak out. Is that okay?
Yes, sir.
But this volume integral should be equal to the surface integral. according to our Gauss divergence theorem, am I right? Volume integral of what you call divergence of a vector field, okay? Because this volume is the whose boundary is this surface, am I right? I have taken the same sphere, okay? So this inside region is the volume that I have taken, okay? So into d2, that's equal to closed surface integral of v bar dot dA bar, am I right? Check this out. This is small v, this is capital V. Is that okay? Can you find out the difference? Okay, this is small v, this is capital V, volume, so total volume. So these two should be equal according to our Gauss divergence theorem, or I think fundamental theorem of divergence, isn't it? But here, since divergence is 0, we got what you call this volume integral 0. Again, we got some inequality, isn't it? Whether Gauss divergence theorem fails here? Speak out. Speak up. So, I mean, give me your idea.
No, sir.
No, it should not fail, am I right? So that's how we believe mathematics, isn't it? Look at here. These are proved, isn't it? These are mathematically what you call well proved what you call theorems, isn't it? That cannot be what you call so that cannot fail, okay, in any situation. Then where is the what you call flaw? I mean, where is the what you call mistake? Where is the defect here? Speak out.
Sir, flux from origin is not equal to 0.
No. Again, I have yeah, flux is non-zero. That's equal to 4 phi. Yeah, that's okay. Then
And outside, other than 0, it is 0.
Now in this divergence, how did we define the divergence? I think volume density of outward flux. Am I right? That is 0 everywhere except at the origin actually. If you think of what you call this kind of field is generated by, I mean, so that is due to electric field because of charge at the origin actually. Okay, you have a source at the origin here, point source at the origin. This is because of point source at the origin. Is that okay? So that's why this equation is not true always. Okay, this equation is true only at all point other than the origin actually. Is that okay? And now this del dot v, okay, this del dot v, so that is non-zero at the origin, it is 0 everywhere else. And not only that, look at here, since this equality should be valid, am I right? These two should be equal. That's why this should be equal to 4 phi, am I right? So shall I believe this one? This should be equal to 4 phi. So then, again, we have to correct this one. We can write, look at here, del dot v, okay, divergence of this one, that's equal to 0 except at the origin. Except at the origin. That is the correct one actually, because this vector field is not differentiable at origin at all. Because at origin, when you put r equal to 0, you are ending up with a kind of infinity, isn't it? The magnitude is infinity, isn't it? Magnitude is tending to infinity, isn't it? Magnitude of this vector field. So that's why this vector field is blowed up at the origin. So because of the fact that this vector field is not differentiable, it's a kind of differentiation, am I right? Divergence is a kind of differentiation that is not differentiable at the origin. You better say like that. Is that okay? So it will not possess derivative. So, and what you call diverge again, but other than the origin, so this vector field is well defined. Again, you can use your formula, am I right? What 1 by r square, some dou by dou r, VR r square, like that, am I right? You can use this one in case of a spherical coordinate. Is that okay? Whatever the formula, you can use that one, but except at the origin, okay? So that's why we can say this is 0 except at the origin. Then what is happening at the origin, okay? What is the value of this one at origin? That we need to fix from what you call this equality only. Is that okay? What is the value of this divergence of this kind of vector field at the origin? That we need to fix by this one only. We better write like this. This is equal to 4 phi, okay? That should be equal to volume integral of, okay, del dot v d2. Is that okay? So this is 0 except at the origin, and its volume integral equal to 4 phi. The value is 0 except at one point in space, and that volume integral equal to a constant 4, 5. Is that okay? Now to look at here, no well-behaved function. This is a scalar, am I right? Again, once you take a derivative, this is a scalar. That's a scalar field, am I right? No well-behaved function exists where which has a non-zero value at one point in space and 0 everywhere, and whose integral equal to 4, 5, or whose integral is equal to a constant. Okay. So that's why we need to go for defining a function actually. Okay. So this is how Dirac delta is will come into play actually. We need to we need to introduce a function actually here. Is that okay? Because Dirac delta is not a mathematically well-behaved function actually. We need to introduce a function. Okay. So that again this this theorem again is theorem is valid, so that again it will follow the theorem. Okay. So no well-defined mathematical function exists here. Okay. We need to define a function so that these things will happen. Is that okay? Speak out. Now look at here. Let me give an example. This del dot V, which is non-zero at the origin, which is 0 everywhere else, isn't it? Now we have the same situation. Suppose you have a mass, okay? Suppose you have a point mass, okay? Mass is m, point mass. How do you define mass density? Speak out. You have a mass at some point in space. How do you define mass density?
Sir, mass is something which is supposed to change the state of motion of.
No. Don't go for what you call Newton's law or something. What I'm saying is define a mass density of this configuration. Mass per unit volume, isn't it? Other than this position, everywhere else your rho equal to 0, am I right? Your mass density is 0 because there is no mass. But at this position, suddenly there is appearance of mass, am I right? So that's why for a point mass, look at here, at this position, you have infinite mass density. Everywhere else, you have 0 mass density actually. Is that okay? At the point, because it's a point particle, that's what I have taken. Is that okay? So mass density is 0 everywhere. Mass density is equal to infinity at this point actually, because at very short region, so this mass appeared, isn't it? Again, mass by volume, am I right? This volume tends to 0, isn't it? Again, if you define rho as mass by volume, for this mass at that point, okay, mass is finite, but volume is almost 0, isn't it? The ratio is almost infinite. Is that okay? Speak out. And we are at the same situation here, okay? Again, we have a point source here, point source, isn't it? We have a point source here, okay? And again, because of that, these problems are appearing actually. It is 0 and that integral is 4, 5. Is that okay? Now look at here. So I know mass density is infinity at this point. Mass density is 0 everywhere else, okay? But what is the total mass rho d2? Speak out. That's equal to m, am I right? There is a mass. Total mass is there. Even though mass density is infinity at some point, 0 everywhere else, you have total mass, am I right? You are going to write like this, volume integral. But that mass density is a ill-behaved function. Can I say like this? It's not well-behaved function. It is infinity at some point. It is 0 everywhere else. And this del dot V is also behaving in the same manner. Whose integral is finite, okay? Whose integral is finite, but whose value itself is infinity. No. Again, look at here. Again, if you take a small volume, okay? Take a infinitesimal volume. So shrink that volume to 0, around that point. You have a mass, okay? But you are shrinking that volume d2 to 0, d2 or something to 0. Is that okay? Then look at here. So denominator is low, numerator is finite, okay? The whole thing blows up actually. So that's why I told your rho is infinity for a point mass. But total mass, it is not infinity. Total mass is finite. So totally, what I am trying to introduce here is rho is ill-behaved function, okay? rho is ill-behaved function. It is infinity at some point. It is 0 everywhere else, but its volume integral is finite. What kind of function satisfies that one? Which is infinity at some point, isn't it? And what do you call, whose integral is finite. So again, we don't have any well-behaved function. We have to introduce that function. That is Dirac delta actually. Is that okay? Speak out.
Sir, if
Yeah.
you are taking a point, sir, then, sir, if you are taking a point for which mass density will be 0, then, sir, how can we choose any other point, sir?
No. What I'm saying is, you have a mass here, okay? You have a mass at this point in space, okay? Now, again, this whole system, if you want to write charge density, mass density, that mass density, okay, that's equal to infinity at this point. That mass density is 0 everywhere else because there is no mass other. If you take a space where there is no mass density is 0, am I right? But we need to define the density, isn't it? Because we do what you call spatial integrals here, isn't it?
Okay, sir.
We need to define, we are in the situation to define that one as a function. Look at here. So that's why we introduced Dirac delta.
We are taking some function. Sir,
Again, we have to write that one as a function
we are
actually.
taking the density of that, sir.
Because we are doing some integrals and all, isn't it, with respect to space. Are you getting my point? So that's why it is required to define as a function. So we introduce a function because in mathematics there exists no function which does this kind of job. Is that okay? Now look at here, that should be equal to 4 phi, am I right? So now we shall just stop here. Let me quickly discuss some part of what you call Dirac delta. I hope you already know about Dirac delta, am I right? So shall I so quickly continue, am I right? Dirac delta of x dx, it is defined like this, or you can define Dirac delta like this: delta of x is equal to infinity at x equal to 0, 0 otherwise, isn't it? And that again, integral minus infinity to plus infinity, delta of x dx is equal to 1. Speak out. Area under the curve equal to 1. It is a spike at x equal to 0. That's how we defined one-dimensional Dirac delta, isn't it? Speak out. So it is even function, okay? You have to, you can draw it as a Gaussian actually. Isn't it? And similarly, if you want to define delta of x minus a, how did you define? At x equal to a, it is infinity, am I right? It is infinity at x equal to a. It is 0 otherwise, isn't it? That's how you define, again, its integral over the region, so throughout x-axis, okay? That's equal to 1, isn't it? This is how we define Dirac delta. We introduced Dirac delta because it is required, isn't it? It was required, isn't it, in case of quantum physics also. Now look at here. Again, that Dirac delta, actually, this is very important property of Dirac delta. F of x into delta of x minus a dx, am I right? Let me take minus infinity to plus infinity. It need not be minus infinity to plus infinity. It should be neighborhood of a. I hope you remember that kind of point, isn't it? So that's equal to f of a, am I right? Dirac delta will choose the function at the point where it is spike. This kind of property, or I can take it like this: a minus epsilon to a plus epsilon. Am I right? If you integrate in the neighborhood of the point where Dirac delta is spike, okay, at that point also, look at here, this is true. It need not be throughout the region, okay? Delta of x minus a dx, that's equal to f of a, isn't it? I hope I have taken all of these properties earlier. Try to solve some problem. Speak out.
Sir, if I have two roots, sir, two roots.
Again, I think I did share some videos or some notes. Can you just check that out, or just remind me after the class? Dirac delta. You are talking about this one, am I right? Delta of some ax square plus bx plus c.
Some quadrant.
Some properties there that you can split this one into this kind of Dirac delta, okay? So that you can do that one. So let me share that notes. I have written a short note on that one, and just remind me soon after the class, okay? You have to solve that kind of problem, okay? That I will mention in the homework. These are all the what you call important properties of one-dimensional Dirac delta. And Dirac delta was even function. Do you remember delta of minus x is equal to delta of x? of delta of x minus a is equal to delta of a minus x. I hope you know this kind of property. Okay. Now let me quickly get into three-dimensional Dirac delta because we are dealing with a three-dimension here. Is that okay? So that three-dimensional Dirac delta, it is defined like this. Okay. Delta cube of r, that's equal to delta x, delta y, delta z. Is that okay? That means when you put x equal to 0, y equal to 0, z equal to 0, the total thing is infinity. Is that okay? So now look at here, delta cube of r, you can write like this also. You can define it like this also. That's equal to infinity when r vector equal to 0. That means origin, isn't it? It's equal to 0 otherwise. Speak out. You can define like this also. Or similarly, you can define three-dimensional Dirac delta, three-dimension r vector minus some a vector where a is some position in space. So this is defined as that's equal to infinity when r vector is equal to a vector. Okay. Here earlier a was one point on x-axis. Okay. If I have written a vector means that's the position vector. Okay, in space. So that's equal to infinity when r vector equal to a vector, that's equal to 0 otherwise. You have to define three-dimensional Dirac delta like this, okay? And so it follows this property. What is the property? So triple integral, isn't it? You can write delta x, delta y, delta z, okay, dx, dy, dz. Obviously this should be equal to 1, am I right? Because three-dimensional Dirac delta, we have written it as product of three one-dimensional Dirac delta. You can split the integral and you can show that it is 1 because in one dimension it will follow that property. But we better to write this one like this. Integral over all space, can I write like this? I'll write only one integral symbol, volume integral, okay? All space delta cube of r vector into d2 is equal to 1. This is the best way to write this equation. It's a kind of volume integral under the Dirac delta. So three-dimensional Dirac delta is equal to 1. You can say like that. Don't say area under the curve. It's not area, isn't it? Now, as earlier, look at here. This Dirac delta will follow this property, okay? If you integrate all space, integral over all space, f of r, any scalar, what you call, any scalar function here, okay? F of r means f is a function of x, y, z. Or f is a function of r, theta, phi, rho, phi, z, like that, okay? You see, this is scalar only. I'm not writing vector. You can write vector also, but again, this is a scalar only. Whatever I'm writing, this is a scalar function. Don't get confusion if I write r vector. That means I'm referring to x, y, z, r, theta, phi, or rho, phi, z here. Is that okay? F of r into delta of r minus a d2. Okay? R minus a d2. What is this one? Exactly similar to earlier one-dimensional property. That will choose the function at a, where a is some position in space. Is that okay? A refers to some position in space. This is very important property that we need. Integral over all space, but it need not be integral over all space, okay? It can just cover this r equal to a point, okay? Speak out, just like earlier, it need not be integral over all space because again this Dirac delta is 0 other than a, isn't it? That's why you don't have to integrate over all space, you just have to integrate around a, okay? Volume that covers r equal to a. That idea you need to remember, you need to grab that idea. Is that okay? Integral over all space, or you can write like this, integral over the region that covers r equal to a point. Is that okay? So just remember this one, this integral over the region that covers r equal to a point. Okay, it need not be what you call integral over all space. Is that okay? Now look at here. I hope you can keep these properties in mind. Just list out these properties again. Okay, try to work with them. Now look at here. To fix this issue, to fix this what you call problem, what is this one? V bar dot dA bar. That's equal to 4 phi. For that what you call spherical surface, that's equal to volume integral of del dot V d2, isn't it? To fix this issue, okay? So we know del dot V, okay? So that's equal to 0 except at the origin, okay? Where R not equal to 0, okay? But look at here, again, wait a second, let me take one more idea. If you place charge at this point, okay? If you have a source here, okay? Again, you have a vector field means you should have a source somewhere, am I right? Let me take that one as origin. I have a source here, okay? Divergence 0 everywhere else except at this point, okay? This divergence is defined as volume density of outward flux, isn't it? Volume density of outward flux, am I right? If you take infinitesimal volume here, just like that mass, point mass concept, okay? If you take an infinitesimal volume, okay? Again, that flux divided by volume, okay? Limit volume tends to 0. Isn't it? That's how we define this one. When volume tends to 0, this flux is non-zero as long as you cover the source, am I right? Speak out. Flux is non-zero, but you are shrinking volume to 0, isn't it? That's how we define. I think we define del dot V as limit volume tends to 0, okay? So surface integral or flux divided by volume, do you remember? If you shrink this one, again, you have outward flux, am I right? Look at here. You have outward flux because this is along R cap, isn't it? Speak out. There is a source, am I right? You are covering the source. Again, net outward flux exists. Even though you are shrinking the volume to 0, there exists a net outward flux actually. Numerator is not tending to 0, denominator is tending to 0. This is infinity actually. So that's why del dot V is equal to 0 when other than the origin, del dot V, okay? Del dot V is equal to infinity when R is equal to origin, null vector. Is that okay? Not only that, look at here. This is one idea that I got, am I right? Just like in case of point mass, I have just explained that this is infinity, isn't it? Using this idea. But look at here. But that volume integral should be 4 phi, isn't it? That volume integral, that is again obviously again you can write del dot V as Dirac delta, am I right? In this case, look at here, you can write some delta of, so delta cube of R, isn't it? But it's a volume integral that covers origin, okay? That is 4 phi, that is not 1, isn't it? That's why we need to redefine this one. We need to define this one as like this. Look at it, to fix that issue, okay? Because that equality is always valid. That's a mathematical theorem, isn't it? So that's why we don't write it exactly equal to Dirac delta. We write it like this to make that one valid actually. I mean, or again, that this is always valid, but again, this all problem because of some ill-behaved function, okay? So to fix that issue, we are going to define this one as 4 phi into delta cube of R. So that when you do the volume integral, you get 4 phi. Is that okay? That means divergence of R cap by R square, that's equal to 4 phi into delta cube of R. This is very important for us. Okay, it's a kind of fixing kind of thing because again, it's a kind of ill-behaved function actually. This divergence, it will behave like this. Even if you take its original definition, it will behave like this actually. Now this also the same thing, okay, when the 4 phi comes, okay, again this Dirac delta, when Dirac delta is infinity, 4 phi into infinity, that's infinity only, okay, it will follow this property.
Sir, you are denoting origin with a null vector, sir, r equals to 0.
Origin. So as origin is a null vector, am I right? I mean, so position vector of the origin is a null vector, am I right? Is that okay? Now, if you take the volume integral, you will get 4 phi. This is satisfying that what you call equation, am I right? So that's why again we defined, look at here, this is how we defined this will not arise by any derivative or divergence formula. Remember, divergence formula gave us 0, isn't it, earlier? You have seen that one. So this should be defined, okay, so that again this theorem is consistent, okay. Now again you can take one more thing. So suppose if you want to take what you call divergence, okay, of r cap by r square, what would you do? Speak out. So this is because of charge at somewhere else, am I right? Speak out. I have charge here, okay, r prime vector, okay. So this is filled here, this is italic r, so this is r, am I right? Q here. Wait, this kind of thing will come for the what you call for again in the electric field where charge is not at the origin, it is somewhere else. Is that okay? So what is that one? How do you write that one? Speak out. Can you just grab the idea?
So can we write R is equals to R minus R prime in the form of R minus?
You can write like this, but again I need this one. How do you define this one? How do you define this one? So it is defined like this actually. Again, del dot, think over it again, till I too need to think over it, okay. That's equal to 4 phi delta cube of italic r again. That means when italic r equal to 0, that means you are at the position of the charge, this divergence blows up. When italic r is non-zero, that means you are at some other point other than the charge, that is 0. That's the meaning, okay. You can take that idea, okay. Most general one. Now remember one more thing, whenever you take this kind of derivative, okay, look at here. If you take derivative means derivative of some variable, that's what you are taking, am I right? Here r is variable, position in space was variable, okay. So here also this r is variable, this r prime is not variable. Again, I'm discussing kind of electrostatic situation here where this is not variable, but this point is what you call movable. You are taking the derivative of some function at this point, okay. At that point, what you call, again, you are, again, whenever you take derivative, you take neighboring points, am I right? In calculus, you take some neighborhood and all, then you define some limit or something, am I right? So that's why when you vary this point, this r prime is not variable, but this r is variable, remember. Is that okay? If you write this r vector is equal to r vector minus r prime vector, this r prime is constant, this r is variable, whatever the derivative we take here, that is with respect to r actually, okay. Anyway, here this is we gave it by a definition, okay. I think in the gradient problem itself he mentioned that what you call some question, am I right? Again he mentioned some gradient of some italic r, okay, and some del prime, he mentioned del prime of some italic r or something, isn't it? Do you remember? One is derivative with respect to xyz, that means derivative with respect to r vector. Other one is derivative with respect to x prime, y prime, z prime, derivative with respect to r prime vector actually, okay. Those are two different things. Just try to solve that problem again soon after gradient, okay. So there is some problem, just try to solve that problem. So that's why again here, whenever we write del, okay, del dot, del cross or gradient or something, okay, that means we are taking derivative with respect to x, y, z. Okay, we are taking derivative of some spatially defined field, am I right? Derivative of some field, scalar field or vector field. So that's why that is derivative that is with respect to x, y, z actually, whatever we write del here, okay. So if you want to take derivative with respect to this x prime, y prime, z prime, this point, okay, x prime, y prime, z prime, you are going to write some del prime here. That is also needed, okay, in case of what you call, I think, polarization chapter. Is that okay? We do the derivative with respect to the, what you call, source also, source point also. But here we don't do derivative with respect to source point, because source point is constant, okay? Source is not variable, but we take derivative of some field which is defined at some spatial point from the origin. So try to grab that derivative idea, what kind of derivative that is, okay? Now, I don't know whether you remembered or not. So this gradient of 1 by r, gradient of 1 by r, anyone speak out? What is this one? That's equal to r cap by r square. Is that okay? Now, del of 1 by italic r. This is scalar, okay? What is this one? Del dot r cap by r square. Wait a second. Am I right or one more negative sign? Solve those problem again. I think you solved almost 1 week ago, isn't it? Speak out. These problems were there actually. Minus, I think. Okay. So minus, that's equal to minus 4 phi delta cube of italic r. Okay. You can generate one more relation. Laplacian of 1 by r. That's equal to minus 4 phi delta cube of r. Okay. It looks like Laplacian can be defined, okay? No, again, you can't define that one because this derivative doesn't exist when italic r equal to 0. Be careful, okay? So can you just write this down? Minus 4 phi delta cube of r. One more relation. So that's why, again, I hope you understood some points here. Whenever we have a point charge, let me try to give a link with what you call electrostatic. If you have a point charge, okay, suppose if that point charge is at the origin, how do you define charge density? Now, how do you define the charge density? Speak out. You know one thing, okay, you have a point charge here. Total charge is again rho d tau, okay. If you integrate over this region where you have a point charge, you get Q, am I right? Total charge, you know Q. But it is restricted to a point in space, am I right? How do you define a charge density? The charge density should be defined as Q into delta cube of R. So that when you substitute this one, integral of delta cube of R that's equal to 1, you will get Q. Or if you have any charge somewhere else, suppose, okay, charge is here, Q. You can just define R prime vector. Now how do you define charge density? Speak out for this configuration. Q into delta cube of, speak out. R minus R prime. Okay, that means when you take this point at this point, again, if you integrate with respect, no, look at here, integration with respect to d tau, isn't it? That's what we are doing, d tau. That means integration with respect to this x, y, z, not x prime, y prime, z prime. Okay, try to grab this one because so that later I can explain the concept very quickly. Is that okay? Do you remember while writing the electric field, I have written d tau prime? Do you remember that one? That was different. That was we had a what you call continuous charge distribution. We were integrating with respect to this region, okay? That was different. But here we are integrating some divergence of a vector field here in this region, okay? By taking some volume or something, remember. So that's why. So if you integrate this one, okay, around a region when r equal to r prime, okay, around this region, okay, integral of rho d tau, okay, if that covers any volume which contains that region, is that okay? That means this r is variable, okay? If you are integrating over a volume, means this r is variable. If that covers r equal to r prime, okay? So r, just write it as a actually, write it as vector a, then write it as r prime. Again, in case of electrostatic, we write it as r prime, isn't it? Is that okay? This is how you define point charge. So have some idea. There are some questions which will give you these ideas, okay?